প্রবলেম হচ্ছে প্রশ্ন করতে পারবেন না।
প্রশ্নটা যেটা করতে হবে, ওরা কমেন্ট করবে
ওই চ্যাট বক্স থেকে,
চ্যাট বক্সে কমেন্ট করবে, ওখান থেকে একটু ডিলে হবে 5 সেকেন্ড 6 সেকেন্ড মতো, তো সেইভাবে আমাদের তারপর অ্যাড্রেস করতে হবে। তো ওটা আমি কোঅর্ডিনেট করে দেবো, অসুবিধা নেই। আচ্ছা, আই থিঙ্ক আমরা ইউটিউবে লাইভ হয়ে গেছি।
আচ্ছা, ঠিক আছে। আমাকে তো কিছু করতে হবে না, তাই তো?
না না না, আপনাকে কিছু করতে হবে না।
তাহলে 3টে তো বাজে, 3টে 1 তুমি শুরু করতে পারো।
Okay, so good afternoon to one and all. So very thanks to everyone who are here with us, and also to our viewers on YouTube Live. So basically, as you all know that this webinar has been organized by Project Cantilever. So let me just brief you a little bit about our initiative. So basically, the idea behind Project Cantilever is that our aim is to inculcate the culture of science in our society more than ever. So we aim to do this by bringing young researchers and young students with active experts in the field by conducting these various seminars and online workshops, all free of cost. So today is a very special day for us because we have Professor Majumdar to give us a talk on black hole mysteries, which was decided on this very special occasion of the 2020 Nobel Prize in Physics. So before that, let me just introduce Professor Majumdar. So Professor Majumdar did his doctorate from Brandeis University in 1981. And after that, he did numerous postdocs all over India and abroad. And then he first joined as faculty in the Shah Institute of Nuclear Physics, and then various other institutes. And finally, he is a senior professor at the Ramakrishna Mission Vivekananda University in Belur. And the most important thing is that, which I would like to highlight, is the fact that his popularity among students and young. So basically, that is simply due to his very approachable nature and also his eagerness to help out the students. And I can safely say that his popularity among students is much greater than his popularity among colleagues. Okay, so without further ado, we'll just start with the lecture. So I invite Professor Majumdar. So a heartiest welcome to you. So you can now present, you can share your screen, and you can start with the talk.
Thank you very much, Akash. I'm really grateful to Project Cantilever and appreciate the work they are doing to spread scientific consciousness among young people in the country. It's a very, very necessary task, and Cantilever is doing a great job with this. So I'm also grateful that I have been invited by Cantilever to discuss this year's Nobel Prize. Now, of course, I think the reason that I was chosen, well, apart from the fact that my colleagues don't think of me too much and my students do, as Akash said, I think that one of the reasons is that some of us have gotten into a black hole, gotten into black holes, I should say, and have not been able to get out. Okay. Now, if that sounds familiar, I think it is supposed to sound familiar. So basically, I have been inside a black hole for several years and feel completely fascinated. And I was struck by the fact that this year's Nobel Prize was exclusively given for research in black holes. Although, if you look at the 3 Nobel laureates, and especially the Nobel Prize citations for this year. Roger Penrose, Sir Roger Penrose, professor at Oxford University, of course, the citation reads, for the discovery that black hole formation is a robust prediction of the general theory of relativity. Now, this is absolutely the thing. I mean, I think Sir Roger has been involved in black hole research since the 1960s. And the Nobel Committee decided to honor him for a paper which he wrote in 1965. It's a bit late in the day, I would think, but better late than never, because this is such an important paper, and I shall have the honor to talk about it. The other 2 Nobel laureates who shared the prize with Sir Roger are Reinhard Genzel, professor and acting director at the Max Planck Institute for Extra-terrestrial Research, and also a professor at the University of California, Berkeley, and Andrea Ghez, who's a professor in astrophysics at the University of California, Los Angeles. And for them, the citation reads, for the discovery of a supermassive compact object at the center of our galaxy. Now, I would just like to draw your quick attention to the fact that while for Sir Roger, the citation does have the word black hole, for Professors Genzel and Ghez, in fact, it doesn't. So that should tell you something about what they have discovered. My task today would be to tell you, and by you, I mean those of you who haven't really had the occasion to work in black holes, which excludes a lot of my friends in the audience, and I feel ashamed that they are there because they could do a better job than I on this. So this would be really for people who want to know, what is this about? What is a black hole? Why does it deserve a Nobel Prize? That sort of thing. And see, the point is that a very long time ago, there were 2 gentlemen, John Michell, and I think he was some kind of a priest in UK, and of course, Simon de Laplace, who is a well-known physicist and mathematician in France. And they, not exactly together, and have given the years, came up with the concept of a dark star. This concept was based on Newton's law of gravitation, in particular on the escape velocity formula, which I suppose most of you, I say most of you because most of you have gone to school and have completed up to class 10, up to Madhyamik, secondary education. And in that, you all definitely must have seen this formula. What is this formula? Well, basically this formula is a formula for the velocity with which you must throw an object such that it escapes the gravitational field of the Earth, let us say, or any object. Sorry, there seems to be a problem. Sorry, is there a problem? Is Akash there, please?
Yes, sir, I'm there.
Can you see the screen? Because there is some complaint that...
No, we are able to see it, but few people are not able to see it live. So we are taking care of that. You may continue, sir.
Okay.
I think they need to... We'll get it solved.
So, but people on the Google Meet can see it.
There was a problem even for us, but now I can see it.
Okay. Oh, you can see it, right?
Yeah, but it started just a couple of seconds back.
Now can you see it?
Yes. Yeah, we are able to see it.
Everybody?
Yes, we can see. I can see.
Well, I'm only come up to the third transparency, the third slide. So is this okay now? Can everybody see this?
Yes, I can
look,
see.
I mean,
Yes, sir. Yes, sir. In
there's not
Google Meet,
much
there
I
is
can
no
do.
problem. But
Is
yeah,
there
we're
a
able to
problem
see
with
it, sir.
YouTube?
Actually, few people are having problem, but others are able to see it. So I'll just tell you to continue.
Okay, so if you want me to slow down or something, I can do that.
No, sir. That's fine. Because in YouTube, you can. It's getting recorded, so there's no problem with
Okay,
that.
okay. So I shall continue then. All right.
Yeah.
Yeah. So I was saying that there is this formula for escape velocity. It's a very simple formula, and I have given the formula here: 2gm by r square root. And as you can see, if I decrease r, the escape velocity will increase. In other words, if I reduce the size of the gravitating object, reduce its radius, make it more dense, as it were, then the escape velocity will go on increasing. And you can continue this process in such a way that you reach a critical radius, which is called the RS. Well, I'll tell you what S is later on. So RS is 2gm by c squared. When you reach that radius, then the escape velocity is the velocity of light, which means that if you have been able to squeeze the gravitating object to that radius, then the escape velocity is the velocity of light. So if you were able to squeeze a little bit further, then the escape velocity would exceed the speed of light. That would mean that gravitating object, well, speed would trap all the light. This is what these two gentlemen, Mitchell and Laplace, thought. And they said, therefore, that massive stars with small radii would likely to be invisible. Another way of saying it is that there would be a critical density of stars, of mass in the stars. If you exceed, then these stars would become invisible. So maybe there are a lot of these dark stars in the sky whose existence we will never know about. Now, is this right? Is this correct? Remember that this was based on Newton's law of gravitation, as I mentioned. And Newton's law of gravitation, in its turn, is based on on the Galilean principle of relativity. What does the Galilean principle of relativity say? Well, before I get to the actual principle, which is written down in this slide, I would just like to tell you a little story about this thief. You see, my house is at the corner of a long, narrow lane, and the poor thief who had entered my house, the chore then got out from the house and started running down the lane. And of course, then there were various people chasing the chore. So everybody was running with a constant velocity. So the graph here in the x-axis is time, and in the y-axis is the position, the displacement of the chore as perceived by the person who is running after the chore. So the first one was this big fat chowkidar. This is the magenta line here. I hope you can see my cursor. So this magenta line here is this chowkidar. And for him, the chore is running pretty fast. But then we have different policemen and women maybe with different speeds of following the chore, and they draw these different lines and all the way up to here. And we find that none of them can catch the chore, so we have to contact a champion runner like Milkha Singh. The only problem is Milkha Singh does not ever catch a chore. He just wants to see whether the chore can run as fast as he can, or he can run as fast as the chore. So you see the t-axis, the time axis would be the graph that Milkha Singh would draw for the displacement of the chore. So because he's running with the chore has no displacement with regard to Milkha Singh. And then we say, okay, Milkha, kaam nahi hua, so let us call Usain Bolt. And of course, Usain Bolt is a great runner, and that is the graph corresponding to Usain Bolt. And you can see that the displacement corresponding to this graph is negative. Why? Because Usain Bolt easily overtakes the chore. And you can continue doing this with bigger and bigger followers of the chore with faster and faster speeds, and absolutely no restriction on how fast you can go. Okay, so this picture tells you that for every time there are an infinite number of possible displacements of the chode depending on who is the observer. Okay, it also means that one of these lines, for instance, this one would correspond to a line bigger than the speed of light, because there is no restriction at all on the speed of light in Galilean relativity. If that is the case, then of course, any conclusion based on the speed of light can be changed by going to another frame, because in that frame, the speed of light would change. It follows that from a Newtonian perspective, we are not able to then decide whether dark stars exist, because the velocity of light has no special significance, no special conceptual significance in the theory of Galilean relativity. So this is pre-Einstein theory of relativity. Galileo Galilei was the first to think about it. And you can see what I've changed here, what I've written here, all velocities, including the velocity of light are relative. Okay, that's a secret. But all that changed, as we know, when Albert Einstein formulated his special theory of relativity. Light acquired a completely different status. In this picture, I've changed the space and time axes of the previous diagram. So in the previous diagram, the x-axis was vertical and the time axis was horizontal. In this one, as you can see, the two green lines correspond to time and space, the time being vertical and space being horizontal. But it doesn't matter what they are, because the real hero in this picture are the blue lines corresponding to light paths, light rays propagating in the future. Now, I should tell you that there's also something in the past which is an exact replica, a reflection of this diagram about this axis. But we don't have to worry about the past, because nobody can go to the past. We can only go into our future. There's another reason for it, but let's me not get into that. So if you look at this, then on these light rays, if you take any point whose coordinates are x and t, x for the space coordinate and t for the time coordinate, then x will always be equal to ct. That just means that these are light velocities, these are light paths, light rays. And this is true for every observer. That's a key point here. In special relativity, the velocity of light is not relative, it's absolute. Okay? Now, the root of this absolute nature of the speed of light lies in the nature of electrodynamics, which was formulated by James Clerk Maxwell. So it's not without a root. It's not an empty slogan which Einstein pulled out from nowhere. It's firmly grounded in Maxwellian electrodynamics. So we have only spoken about this part. So this is x equal to ct, and for all these other lines, the ones in brown, x is less than ct. This pink hyperbola, which you see here, this pink hyperbola actually designates a single event observed by different observers. And you can see that space and time coordinates both change, okay, even though the speed of light is constant. Okay? And this diagram is extremely full of meaning, because using this diagram, you can almost deduce all the consequences of special relativity. In the bottom here, I have drawn a few spheres. So you're supposed to think of these as spheres of light. So you're supposed to think of a candle being lit here, and then as time goes on, this ball of light which emanates from the candle keeps moving in this direction. Now, if you look at any of these balls of light at any instant of time, you can see that there are three classes of observers. One class who are already inside the light ball, who've seen the light emanating from the candle. Another class of observers who are just on the fringe, on the boundary of the light, who are just getting to see the light. And another class, like the flag bearer here, does not get to see the light from the candle until this moment of time. So the time is supposed to be thought of as going in this direction from left to right, so that he gets to see, or he or she gets to see it much, much later. Okay? So this also tells you how different observers see the same event. Okay? just like I mentioned earlier. Okay? So this is about special relativity. Light has a very supreme position in special relativity. But I shall not talk about special relativity today. Indeed, most of you probably know quite a bit about special relativity. So what I shall talk about is curvature. All of you are familiar with space curvature. What is space curvature? We'll take a bed sheet or some such piece of cloth and put such heavy objects, be they metal or wood or whatever, into the cloth, and you will see a kind of curved surface forming here. So you see this curve here, and to a lesser extent, depending on how heavy this mass is, you'll see the curve here. So the curvature of space is something very similar, except that we don't have a bed sheet. It happens automatically. The mass will curve space just like we have shown here. However, our interest is not particularly with space curvature. Because one thing which I should have mentioned here, you see, is that the moment we deal with such diagrams, these are called space-time diagrams. The word space-time has already come here. So that just means that you can't separate space and time anymore. They're always mixed together. It's like saying, if you say, yeah, I will go to my Mashid Bari, the question will be when. So on the other hand, if you say, I'm leaving tomorrow, then the question will be, where are you going? So these concepts of space and time are actually always mixed up, because there is no such thing as an absolute time. If you have velocity of light as absolute, there is no way that time is going to change. Indeed, these points, you can see this point compared to this point, you can think about this point as a kind of rotation of the time and space axis. So time and space will change. The velocity of light always remains unchanged. So I've taken that same diagram, the light cone, the light frame diagram, and tried to show you what space-time curvature will do. On the left, we have a situation where we have copies of the same diagram as here. Okay, it's just this diagram copied over. Main diagram, I didn't want to draw what's inside, but just the fact that the light rays are going in this kind of angular situation. So these are light rays, and this is what we will call curvature-free or flat space-time. But if we have space-time curvature, how would we see this? How would we depict it? The only way to do this is to talk about, pictorially, is to talk about the bending or tilting of these light cones. You see, if this is a source, this is a mass or some gravitating object, then what you see here is that these are getting tilted. Now, what does this tilting mean? If you look at here in the flat space direction, and suppose you want to look at how, suppose this is the time you begin with in correspondence with this. So time is flowing in the vertical upward direction. You are here, and the light comes from there, so that you just extend this, and wherever it meets here, that is the time from here, you will see this light ray. Same here, you see the light ray here. But you can see immediately that if you look at this light ray, it's going to take you very, very long, because it's going to meet this vertical line way up here, and this will take even longer. So you see, what the tilting is doing is to make light go slower and slower as far as the external observer is concerned. And you can probably guess that there will be a kind of tilt for which you will never see the light which is being lit here at this point. And we'll come to that in a moment. So this is the idea of space-time curvature. What does space-time curvature do? Space-time curvature makes the light cones tilt. So light will now go along curved paths. And you can ask, what causes space-time curvature? And this is the essence of the Einstein equation. Einstein was the first to argue that there is no gravitational force. There is only geometry, a curved geometry of space-time, which is produced in this following equation. So left-hand side, you have space-time curvature. Right-hand side, you have anything which has energy or momentum density. Mass is, of course, included in this definition because mass will have energy density. Mass times c squared is energy. And then if you look at the energy per unit volume distributed over a volume, that will be the energy density. And similarly, there's also momentum density. So this quantity here tells you that even very bright light, which has energy and momentum but no mass, certainly has energy momentum density, would cause space-time curvature. So this was a fantastic equation because suddenly we realized many things. For instance, these are the consequences. What I show here would look like elliptic motion of planets around the sun, except that this is one planet, you see, let's say the Earth, or could be, actually it's Mercury. And it's one planet, but then you ask, why so many ellipses? Because, you see, these ellipses, in the case of Einstein's general relativity, it turns out that there's not a single ellipse, it's not a closed curve anymore. The ellipses are moving, as you can see here. So this is immediately an important consequence. This was a consequence which baffled many people earlier, and before Einstein came along to do the calculation and show that this perihelion was precise. Similarly, there is this important consequence of light bending, very, very important for us, but I've already alluded to it by showing you that light cones tilt near the presence of something which carries energy momentum density. So there you see light bending. This is the Earth, and this is some star behind the sun. You can't see it except for a total eclipse, total solar eclipse. Then everything becomes dark here, and so light can travel. But if the sun did not bend the light would simply carry on. But now you can see it come down. So light bending is another established fact, established consequence of the theory of relativity. Another consequence is that light changes color. So if you have a star which is giving you light, and it starts off as being blue, and as the light moves towards you, because of the gravitational, the curvature here, the light becomes redder and redder. So this is called the red shift. If the light was coming from something which was moving, so this is because the Earth is not moving towards you, but if this was moving towards you, then the light would be blue shifted. Okay, and I should skip that and that because I already discussed it. This is the bending of the light cones in the presence of a gravitating object. I shall now come to another story, that of Carl Schwarzschild. Schwarzschild found the first exact non-trivial solution by assuming that the space-time is spherically symmetric. That's the only one assumption he made, that space-time is for absolutely nothing, for no mass, no energy, nothing external. He just said that if you take the Einstein equation, plug the right-hand side to 0, you get a spherically symmetric solution, which we call the Schwarzschild solution. The story about Schwarzschild is that he derived this solution when he was dying due to typhus, which he contracted during the First World War on the Eastern Front. He was a German soldier, contracted this deadly disease, and while he was dying, it was very painful. He wrote down this solution and sent the solution to Albert Einstein, who was overjoyed because he did not expect to get such a beautiful solution. What is the nature of the solution? Well, I don't have too much time, so the solution is characterized by a sphere. Now, this sphere is not a sphere of, not a ball of mass of any material. It's a geometrical sphere. It tells you that there's a scale, there's a size of the sphere, okay? And things are different between the outside and inside, okay? And on this panel here, what we are showing is the same sphere, and we are showing a circular orbit. So if you're really quite far away from this object, which is a sphere at Rs, where Rs can be written as 2gm by c squared. So there is some mass m associated with the sphere. By the way, some of you will remember that this is the same formula you found from the escape velocity, but it has nothing to do with it. It's a completely different way of arriving at it. And there's also the kind of planetary motion around this sphere. Okay, so if there's a test object, then it will follow elliptic paths like that I've shown here. So outside of this object, things look as if you have a spherical object which is like a gravitating object, but it's a space. It's a space-time really. There's no object there. Okay. And this carries on. There are further properties. One of the properties is that it's a one-way membrane. Things can go inside. Like here I show a particle going inside, radial plunge it's called. It's radially plunging into the spherical region and doesn't come out. Same here, a light ray goes in and never shows up. That's weird. It's a kind of sphere which has so much curvature, not that much curvature, but still sufficiently large curvature. So these paths would bend so much that they can't get out. So these guys do something inside, but they can't come out anymore into this region where we are. So if you have an object like this, we are certainly located here. We won't be inside. We are located outside of the spherical space-time. But inside, some funny business is happening. Then there's other thing. Suppose you threw something, including Partha Majumdar, towards a black hole, then this, in the frame of the observer, like you threw me towards a black hole, you will see that it takes me forever to reach the black hole. Okay, I'll tell you in a minute how it does. What you will see takes forever. That just means that the distance, the spatial distance in that frame is infinite. So it's like the black hole horizon, although it seemed like it's not so far away, it's actually infinitely far away. And what you see is right here. So this is, I've worn a blue kurta, blue Punjabi. So this is me. But as I go towards this region, R equal to RS, the surface, you can see me getting taller, unlike Amitabh Bachchan. And you can see the color changing to green, which is towards the red. Here now I'm the size of the tower, big long tower, Burj Khalifa. And of course I'm dead by then because I've been stretched to the size of Burj Khalifa. I won't survive. And you see the color has changed to yellow, and this is red. So you see this happening, my color changing and I'm being stretched. These are called tidal stretching. And yet you won't see me actually enter this line. This is the horizon, or the R equal to RS surface. Okay. Here, on the other hand, I have tried to draw what the mathematics of the Schwarzschild solution will tell you about the inside of the sphere. What it tells you is that this inside is actually a very dynamical, very catastrophic situation because it is shrinking to smaller and smaller sizes. It's a shrinking geometry. What do you mean by shrinking geometry? Well, all of you are sitting in rooms. Imagine the walls, the ceiling, and the floor sort of coming together. It's a scary situation, right? And you can't stop it. There's nothing you can do to stop it because this is gravity at work. Okay? Now, this kind of a funny situation was enough for Albert Einstein, who was very happy with the solution, but by that time, all the funny business at R equal to RS have not been discovered. So he was saying that, well, he wrote a paper when he tried to argue that this R equal to RS surface is something which is, he named it the Schwarzschild singularity, by meaning that it's a kind of very uncommon situation at R equal to RS in the sphere, and it's unreachable. It cannot be reached. Okay? Now, Einstein wrote this paper in 1939, and 14 years later, there was this man, Reinhard. What was Reinhard doing at the time? Well, he had been fired, well, he's not been fired, but his tenure at the Cultivation of Science in Kolkata as a research officer came to an end. So he was in Ashutosh College on a leave vacancy situation. Some of you who are senior would know what a leave vacancy is. That is a job for like a year, and after that you're jobless. And then he wanted to do general relativity. Okay? And what did he do? He started off by criticizing this paper of Einstein. You know, we did ask him, sir, and he said, how did you have that kind of guts? And he said, well, you know, এটা সবসময় দুঃসাহস বলা চলে আমরা একটু দুঃসাহসী. He said it's I don't know how you translate দুঃসাহস, a kind of super guts, okay, that you really want to go beyond everything and you want to play a gamble and see where it goes. So his doubt and it turned out that he was very right and Einstein was wrong, he had an unreasonable doubt that the problems that are equal to our sphere are all unphysical. It has to do with the selection of a frame. By selection of a frame, I mean selection of a laboratory. You see, every laboratory is a kind of frame, but every laboratory may have a different setup, like a coordinate axis, let us say. And if that is separate, then these things will change. So there of course, are frames or laboratories where R equal to Rs is no problem at all. So Raichaudhuri in this paper was the first to draw attention to the fact that the real problem with the Schwarzschild solution was not R equal to Rs, but at the center of the sphere, R equal to 0, where he was able to argue that the curvature goes to infinity. Okay, wait a minute. We were talking about Einstein's theory, we were talking about a space-time as a continuum. Continuum means that there is not a single point in the space-time where things are funny. Now here it is at R equal to 0, which is a point in space-time. Raichaudhuri was telling us that the curvature becomes so large that geometry breaks down, that no concept, okay, there's no concept of physics anymore because physics depends on geometry. The geometry breaks down because the space-time continuum breaks down. Now this was something which people were really scared about. Although mathematically it was always there, but to think about it like this was really scary. And some people said that, well, maybe because you're working with this one solution of Einstein's equation, which is the Schwarzschild solution, which has this special property of spherical symmetry. So what if you decided to abandon the spherical symmetry? What if you decided to go to space-times which were more general and did not have this symmetry? So that's what then Raichaudhuri decided to study. And this is what he came up with. He was looking at the paths of particles as well as light rays in a general curved space-time without any assumption of symmetry. And he was able to work out an equation called the Raichaudhuri equation, which would tell you that starting with some surface, with some time, like with a fixed time surface in the past, if you let these particle paths or light rays evolve in time to the future, okay, then would they converge or would they diverge? It's like a problem in optics, which even high school students must be familiar with. You have these lenses which converge as well as which diverge, light rays. So this is that problem now posed for curved space-time, okay? And what Raichaudhuri was able to show is that if they converge, then you have the phenomenon of caustics in space-time. Now this is again something which may be familiar to some of you students who do optics, because you see caustics in your glass. If you put your glass of water in sunlight, you can see caustics on. But we're not talking about caustics in space, you see. What do caustics in time mean? So let us look at this example here. So these are three observers like you and me with mass who are on converging paths. For each of these observers, when they're not converging yet, these are the light frames, okay? And the light frames are quite distinct. But now you can see that if these paths do converge, and then if they come out, whose path would you then look to talk about future and past? So the light cones actually tell you about future and past. I've already mentioned that. So your entire space-time structure at any point is given by the local light cone. But if they converge, then you have an ambiguity, don't you? Whose light cone do you accept? This guy's, or this guy's? And it is this ambiguity which Raichaudhuri's equation leads us to. And the question is, do they signify a singularity? Now here the answer gets to be a little shady because sometimes it does and sometimes it doesn't. And there is a huge problem. But Raichaudhuri was not interested in writing down theorems as to when singularities occur. They didn't. His main aim was to find, because he loved general theory of relativity, he was unable to accept that general theory of relativity would have a singularity as a kind of inherent characteristic. Rather, he felt that there must be realistic space-times which are free of singularity. And he wrote a lot of papers, did a lot of research in trying to find such space-times by changing Einstein's theory a little bit, including things like torsion and so on, and he did not succeed. Okay, so this is one of the problems. But about 12 years or 10 years later, we have our hero, the Nobel Laureate Sir Roger Penrose. And here this picture is of a young Penrose explaining to us a completely different approach. You see, prior to Penrose, most of us, most of the relativity community had relied on solution of solving equations. Okay, that was the ostensible way of doing general relativity. Now, Penrose first told us that no, you can do general relativity by drawing diagrams. And this is kind of funny. You draw pictures and you handle such a thing as general relativity? He said, yes, you can do it. He also introduced a branch of mathematics called topology. Topology is about deforming surfaces, okay? Where until you break them, you don't break them in topology, but when you deform surfaces continuously, what happens to various paths and so on the surfaces? So he brought topology back into the game of general relativity, and he came up with some fantastic concepts. I shall illustrate one of the concepts here, the concept of a trapped surface. On the left here, so this vertical axis is the time, the flow of time vertically upwards. This is our familiar special relativity light cone, and I show you two surfaces at two distinct times. These are two-dimensional surfaces, closed surfaces. And you can see easily that these surfaces are growing. They're growing in volume because the light rays emanating from a point in special relativity diverge. However, we are talking about a different situation. We're talking about the Schwarzschild solution. You remember already that I told you that Schwarzschild solution has this contracting geometry. And this is what made Roger Penrose proposed the idea of a trapped surface, and here it is. So these are again light rays, but here you can see the light rays are actually converging. And this is what a trapped surface is. So the light ray which falls orthogonal, these light rays falling orthogonal. I mean, I should apologize to my expert colleagues because I'm breaking down the language of pure mathematics into something very simple so that, I can carry my audience with me. So these are two-dimensional surfaces on which light rays come. This is still a space-time diagram, there is time. But these are these are light rays in the future direction. So you can see that in a contracting geometry, the light rays cannot go outside. So suppose you are here somewhere. This light ray will come here. But you can see that this light ray, because it has been bent by this contracting geometry, these are called the trapped surfaces, two-dimensional surfaces, will actually never make it out. Okay? So we have for the first time a situation where something will not reach us. Some light we thought will always reach us from everywhere. No, it doesn't. And there is no mirror or nothing to deflect. Nobody is deflecting that light except for space-time curvature. Now this is a very strange, mysterious concept. Okay? And here I have in what physical situation these trapped surfaces would arise. Okay? The left diagram is directly from Penrose's 1965 paper. What it shows is a collapsing sphere. So we have a collapsing spherical star, which is depicted here, by saying that again this is time. So this is time, I've shown the time. And light, as you can see, when you come closer and closer to the contracting star, light had greater and greater difficulty. In fact, if you look at this line here, the light cones are such that the outside observer does not receive any light from these cones, from the cones here. Okay, and these, okay, when you look at a fixed time, the two-dimensional surface that you get is precisely the trapped surface. So the trapped surface is something which is housed in a contracting geometry. Eventually, there's no trapped surface here. The trapped surfaces start falling after this kind of a situation where light cannot go out anymore. So all the light that is emanating from this point will go inside, and here also inside. the observer will only see light from just outside the trapped surfaces. So there are a whole bunch of trapped surfaces with smaller and smaller areas, and eventually all these trapped surfaces collapse to a point. Now this is a slightly better, more picturesque diagram, but basically saying the same thing. This is the trapped surface. This line here, where, okay, so this is not exactly a very good diagram. So that is why, Penrose is more accurate than this diagram. So if you have a light cone, then the light just travels along this, or it can go inside, but it cannot go outside. So there it is. After this region, when the light stops coming out, whatever object was collapsing, whatever star, has become dark or black. So that's the black of the black hole. And then, as I said, these trapped surfaces contract and contract till they form this blue line, which is the singularity. What is the singularity? It's the same definition. It's where the laws of physics break down. And of course, because the laws of physics break down, I can't even draw a light cone on this blue line. The blue line is supposed to depict a singularity. So the black hole has two definitions. Black, because light is trapped by the trapped surfaces. Light can't go outside. And singularity, where all the laws of physics break down. So a singularity strictly is a statement of our ignorance. We don't know what is happening, because if all the laws of physics break down, laws of geometry break down, we don't know what to do. Now here is a little picture for some of you who may have found the previous pictures difficult. So this is a star which is collapsing, a spherical star. And if you can see these blue lines, that's supposed to be the light which is emanating from this star. And when it shrinks to this size, the light is sort of stuck to the surface. There is a little bit of light going, but it will take a long time to reach outside. And when you see the spring sphere, the light is completely confined to this surface. And that's the formation of what we call the event horizon. So the trapping has started from here. Light is completely trapped within this surface. Now this surface is, of course, does not mean that it's actually a physical surface. If you think of gravitational collapse of a spherical star, as soon as the spherical star reaches this surface, light from the star fails to go outside. It becomes black. But the star does not stop its shrinking. It continues to shrink like this. So you see the event horizon is right there. It's a geometrical surface, R equal to Rs, the same R equal to Rs, but this continues to shrink and shrink and shrink. So the big star has shrunk to a point, okay? All because of gravity, of curvature, because of extreme curvature. And when it has shrunk, it has become something which we cannot understand, some weird thing, something called a singularity, okay? So this is basically the idea of the previous diagrams. And now I shall end this part of the talk with Penrose's impossibility theorem. If we have a smooth space-time, such that for every event in the space-time there's a distinct future and past, every light ray or particle path starts at a definite time and can be extended all the way to infinity, so there's no mirror or any obstruction in the path of these light rays and particles. They can go all the way to the infinite future. At every point in the space-time, we assume that Einstein's equation holds with positive energy density, and the space-time admits a trapped surface. Then Penrose says that it's impossible to find such a surface, such a space-time within the premises of general relativity. So this impossibility theorem is like, Kenneth Arrow's impossibility theorem in economics, but I think that social scientists will, not like this comparison too much, because that has to do with voting behavior and all kinds of things, which I shall not get into right now. So this is what Penrose succeeded in proving, and the proof crucially uses Riccioldi equation, okay? So, if you say that you have a trapped surface, then you cannot accept the fact that your space-time is smooth everywhere, because there is bound to be at least one point in space-time where the laws of physics break down and space-time is no longer smooth, okay? That's the key idea. So one point is bad enough. So you are saying that there is this point which is not a point of space-time. What is it? I don't know what is it, what it is, okay? Of course, this is really bad, but we don't have to worry too much. For the case of a black hole, you see, we will never see the singularity because they are protected by the event horizon. We are all outside the event horizon, so we will never get to see this weird happening at the end of the collapse process. We will never get to see that. Okay? So this is where I end the sort of theoretical understanding, and now you can see that the entire theory of black holes, classical theory, is crucially dependent on Penrose's vision and his analysis using advanced mathematical disciplines like topology and differential geometry, proving the theorem using the Wright-Choudhury equation that singularities are generic in general theory of relativity. In the theory of general relativity, this is crucial because space-time guides every other physics known to humankind. So if space-time breaks down, the geometry of space-time breaks down at some point, then all of physics breaks down. Basically, we are saying we don't know what is going on. The question now is turning towards, now I don't know how I'm doing with respect to time. Akash, my friend, will you tell me how much time I have?
Around, you have 20 minutes.
Okay.
Like 10 minutes to 4, and then you can extend for further 10 minutes.
All right, very good, thank you. I would apologize if I've succeeded in boring some of you, but let me carry on. Maybe things will not be so boring right now, because the question is, okay, all very good, trapped surfaces, black holes, singularity, all that we heard, very nice, but are they really in nature? Do they exist? And how would we know? Because if there's a black hole out there sitting all by itself, there's nothing coming out of the black hole, then you will never know it's there, right? Except when you go very close and then you're sucked in and finished. And then you will never not be able to tell us what you saw, okay? So it's a very, very peculiar situation. And only way that we can know about the existence of a black hole is if there's something else outside a black hole which is sending some stuff into the black hole, be it light or some matter. So there's an interaction of the black hole's curvature with the matter coming from some other star or other object outside a black hole. And this gives out some signals which we on Earth can receive. Okay? And believe it or not, you can receive this. Before I get to that, let me just say that there are two kinds, two distinct kinds, two main kinds. There are also other kinds which I shall not talk about here. There are stellar black holes which are heavy, 5 to 50 times the sun's mass. But there are some fantastic things called the supermassive black holes, which are 1 million to maybe 1 billion times the sun's mass. So there are these amazing kinds of black holes. And intermediate mass black holes, well, maybe they are there, but we haven't seen them yet. Maybe they're there, okay? Intermediate mass between 50 sun's mass and 1 million sun's mass, maybe they're there, okay? Now let me, just for a moment, show you, because, you know, this might be of some interest. And here it is. So just to make you believe that this is not something that only mathematics and imagination leads us to, here is a video of something called Cygnus X1. What is Cygnus? Well, Cygnus is one of the arms of the Milky Way, but this is still 5,000, 6,000 light years away. So this is a constellation Cygnus, and we are now looking at the optical view of this. But in the middle now you see something, so the optical has turned into X-ray. So what we find in the middle of this constellation is a very bright X-ray source, okay? And this X-ray source is unexpected. The Cygnus X1 is the closest black hole to us. And what is happening now? Well, there it is. This is a giant star called the blue giant, and stuff from it, and this is our black hole, Cygnus X1. So stuff from it is encircling the black hole like a huge disk. This disk is called an accretion disk and falling into the horizon. So let me go again. Right there, okay? And as it falls, it gives out these X-rays. Okay, so it's the X-rays is given out not by the black hole, but the stuff that is falling from the blue giant into the horizon, event horizon of the black hole. Okay, so that's something that was astounding. And by studying the characteristics of these X-rays, we are able to tell that yes, what the stuff was falling towards, all the matter and radiation and everything, is not a star, but a black hole, which is nothingness with a boundary known as the horizon. So this nothingness with a boundary called the horizon. We don't know what's happening inside because nothing comes out, but we know that when stuff falls there, it becomes very excited, and that excitation means that the atoms falling in will now radiate X-rays. So that's what we see here. Okay? Now, so that this is something which is experimental, which is observational. But I would like to add that since 2015, you see, there's been another way to detect the existence of black holes, and that is not electromagnetic. If you have a pair of black holes going around each other, okay, then these two black holes going around, merrily around, sort of dancing around each other and becoming closer and closer, will emit gravitational waves. Okay, and in 2015, we were able to detect such gravitational waves sitting here on Earth. Now you can see as they come closer and closer, the green stuff becomes brighter and brighter, and then they coalesce, they merge, and there's a huge big green stuff, green ripples which come towards us. Okay, and we are able to detect this. So this is another way of seeing that there could be a pair of black holes, and the signal that we get from them does not involve electrodynamics at all, no electromagnetic signals or light. Okay, good. So let's go back to this. However, people were interested in other kinds of signals. These are called active galactic nuclei. These are galaxies which are far and far away. The first one on the left, which looks like a little purple thing in the middle, is called the galaxy M81. It's like 10 million light years away from us. And it's a galaxy, but the fantastic thing about this galaxy is that extremely bright. So remember 10 million light years. You can do a little calculation to see how far that is in kilometers. I don't want to do the calculation because a lot of zeros in that calculation after one. Okay, so if you do that calculation, then you find that it's so far away, and yet the center of the galaxy, that is called the galactic nucleus, something is happening here. It's emitting a very strong X-ray, and these blue ones are ultraviolet rays. Okay, so this is M81. The picture on the right is from another galaxy called Centaurus. This is Centaurus A, and you can see there's a dust cloud here. This is just dust cloud, but in the middle is another extremely strong source of X-rays. Okay, these two pictures are very recent, last year, 2019. They belong to a galaxy called M87. This M is for Charles Messier, who was a French astronomer who found all these galaxies, but he just found them as spots of light in the sky. What we've been able to do is to use fantastic telescopy, which is a kind of very large baseline telescopy which involves many components, and using that we are able to see fantastic structure. This one is 54 million light years away, and here see how bright it is, and it's emitting a jet. This is of course not in optical, this is in radio. None of this is optical. This is false color image. So we do the analysis when we want to show it to people, there's a coloration done. And it's coming like this. And this is the photon sphere, the shadow of the photon sphere. So this is the closest one has come to actually photographing a black hole. You see, a black hole, we would like to take a photograph of the event horizon if you could. That would be sort of a smoking gun signal, but we're nowhere there. But remember, this is 54 million light years away, and yet you're able to see. So the light is actually eaten up, the light from the outside is eaten up, leaving behind this dark region called the photon sphere. So this is several times the Schwarzschild radius, R equal to Rs, several times bigger in size. And all of these galaxies, and there are hosts and hosts of them, they all host a galactic center supermassive black hole. The kind of optical observations or kind of X-ray observations or radio observations that you make on these extreme active galactic nuclei have to do with this fact that they all host a supermassive black hole. Of course, this is true for galaxies which are millions of light years away. And you will say, hey, what about the friendly neighborhood galaxy where we live, known as the Milky Way? That's the next question. Is there a supermassive black hole at the center? This is the question, among many other questions, which these two great astronomers, Reinhard Genzel and Andrea Ghez, set out to investigate. So what they did was ask this question, is there a supermassive black hole at the center? And the answer becomes difficult in the very first instance, because unlike these active galactic nuclei, which accrete matter from other stars around them, and so there's always this accretion disk from which stuff is falling into the black hole, and because the matter falling in gets excited, X-rays are emitted, and sometimes radio jets are emitted, and so on. In this case, our local hero, the guy at the center of our galaxy, Milky Way. This is a picture of the Milky Way. You can probably see this guy here. What a wonderful picture of Milky Way that is. This is some water body. This is on Earth, of course. And this is another view of the Milky Way taken, I think, by Hubble Deep Space. Beautiful pictures. But this galaxy of ours is not active. The supermassive black hole, if it is there at the center, is not accreting matter. And therefore, we don't have such powerful signals as we did for M87. You see, when M87 was discovered, this is what kept bugging me. Something 54 billion light years away, and we could see a photon sphere. And yet something which is, well, this one is 25,000 light years away, which is far, far less. And yet there's no strong source of X-rays or radiation coming from this object. So what do we do? How do you know that there is something there? The other problem we have is, so this is the Milky Way galaxy, is our location. See, this is the center of our galaxy, spiral arms. We are in this outer spiral arm known as the Orion arm, okay, right here. There's also the Sagittarius arm, other kinds of Perseus arm. I already told you about the Cygnus. So we are 25,000 light years away. And in between us, okay, and the center of the galaxy are about 2 crore stars. So obviously, if you want to see what is going on at the center, you have to contend with all the light that you're receiving from these 2 crore stars. And this is a huge problem, but there's also a fantastically smart technological solution known as adaptive optics. So the idea is that all this extra stars, the starlight, you don't want to see the starlight because you're interested in what is behind them, the center of the galaxy. But they are emitting the light, so what do? What you do is something called a rubber mirror. Put a rubber mirror in your telescope. So you see, this is the undistorted wave front. This could be atmospheric turbulence or interference from other starlight, and then this rubber mirror adjusts itself. It is deformable. So every time you see that there is some extra stuff which you don't want to see, it deforms itself in such a way. It's very, very smart laser optics. I don't know how to do it. So that this is reflected away. And the effect is miraculous. You see, this is the picture that you would draw from a telescope without adaptive optics. And this is what you would with adaptive optics. You can see the clarity, the improvement in clarity that you get. And it is because of this clarity, you see, that some fantastic things are possible. So even though I told you that our guy at the center did not accrete, okay? However, see, it's really beautiful because even so, we are able to see a star. We are able to see the closest stars And the picture on the left is from the European Southern Observatory, very large telescope in Chile. So this was the group of Reinhard Genzel took this picture. They actually collaborated, but I'm just drawing these two because there are two people who have got the Nobel Prize and they did independent work as well. So this is the Keck UCLA Galactic Center group. They were observing the same star, but Genzel's group called it S2 and Andrea Ghez called it SO2. I don't know why this difference. So I'd like to show you a video, and that will be the last one. Okay, so I'm going to end my talk by showing you the video which these people took. Well, two videos to be honest. They're short videos, so don't worry. Right. Oh, what happened? Right here. Okay, so let me just show you this one. So this is a trip. Okay, we're going now towards the middle of our galaxy. We just passed Sagittarius and Scorpius and going towards the center of our galaxy. Let's say on a spaceship, although this was not really like this. This is, of course, pictures taken at different distances. Okay, and then they are beautifully simulated together. Okay, so keep going and going and going. This is, as I said, 25,000 light years away. Of course, we don't have 25,000 years to talk about it. But as you come closer and closer, you begin to see something's happening. So after a while, you see this huge density of stars goes away, and you come to a sort of clearing, like coming to a clearing after getting through a forest of stars, and this is where you see it. And this is what these astronomers begin to see. You know, this kind of peculiar behavior of stars, they seem to be going around something very massive. Okay? And this is amazing that this is happening. And then they did some simulations, and when they do the simulations, they have these beautiful pictures of elliptic paths of stars going around some point, some region, and this is that region. Now, from the size of the ellipse and the time it takes for these objects to go around, I'll show you another one, you can say what is the mass of this little object, black object here, around which, so this is the closest, this is S2 or SO2, this is the star closest to the center, and you can see that when it's far away, it's typically elliptic motion, it's very slow, and as it comes closer and closer, its speed increases. So this is the center, and then it speeds up like then anything and slows down again. This is a beautiful picture, but this is a simulation after the data, which Genzel and Ghez were able to draw, which proved unambiguously, okay, this was unambiguous proof that there is something which we anticipated. So this is going back to that. Okay, so this is called Sagittarius A star, the object at the center. So it's a super massive compact object, because if it were not so, the stars, the huge big stars S2 and SO2, which are several times bigger than the sun, would not go in fashion. So we have seen the parts of the stars, seen stars, analyzed the light, and we found that they have this peculiar motion, which led us to conclude that there is a supermassive object in the middle. So now the pending mystery is there a smoking gun signal that this supermassive object, compact object in the middle is actually a black hole? The answer is no, because you will need something at least like M87, like a photon sphere. And we can't do that because this fellow, Sagittarius A star, does not accrete. So we might get lucky that Sagittarius A star turns active, and then we can study the accretion disk signals. But what we know for sure is that it's not possible, okay? Or it's not possible for any other object to be like 1 million solar masses. 1 million times solar mass, that kind of mass is never possible. And so suppose it is a supermassive black hole. Do we know how it forms? we know about stellar black holes. I told you Cygnus X1. We know how such black holes form. They form by supernova explosions. I have some pictures, but I can't show you now. I'm out of time. And are we observing signals from a space-time which is not completely understood? Yeah, possibly. We don't really understand black holes. We don't understand the black hole singularity. There are also conundra associated with the horizon. So black holes are mysterious through and through. Is it possible for a stellar black hole or a neutron star to merge with Sagittarius A star? Because in that case, it will become a source of gravitational waves like we have seen in GW 1509, the 2015 discovery of gravitational waves. If that experiment could happen again, if that situation could happen again, that would be very nice because we have another handle on the Sagittarius A star. And finally, as a theorist, I would say that we would like to have improved quantum gravity understanding of black holes. So I guess I should stop here and then attend questions which may arise. Thank you very much indeed for your patience.
Thank you, sir, for this wonderful talk. So it was very enlightening for us and our viewers. So now we'll get to the questions. So basically, I'll tell how will this progress. So people who are viewing us through YouTube, they can comment in the comment box, and then we will just read it out. It will take some time, like 4 to 5 seconds delay, but then we can. Okay, so we have one question from Partho Bhagat. He's asking, what does smooth space-time mean?
Yeah, see, the idea of smoothness is exactly the idea you have of any space without any holes in it. Okay, so if you take a smooth bed sheet, for instance, without any holes, that's a very smooth surface. So I'm giving you a kind of hand-waving definition. So a surface which is very smooth, there's no spike, no problems, no holes, is a smooth surface. Okay? So in other words, when we think of space-time as a continuum, between any 2 points, okay, there is at least 1 point. Any 2 points, so you can think of bringing these points closer and closer, and there's still a point there. Okay? So there is no gaps in the space. Intuitively, that is how we would think about it. There is a mathematical definition in terms of differential geometry, but let me not get into that. I will not talk about it. So, but basically the idea is that, you know, if you define any function on that space, you should be able to differentiate it endlessly. Okay? A function will be completely continuous on that space, and so on and so forth. I don't know if this is a satisfactory answer, but if not, then I would suggest that you can we can discuss it in a more technical language later.
Okay, so there is one more question. Corey is asking, can you please give me a brief definition on information paradox?
Oh,
something outside the
topic. I don't want to get into that because I did not discuss anything beyond classical black holes. So to give you an idea of the information paradox, well, I have to first tell you about Hawking radiation. No, I did not talk about it at all because that is not that does not feature in the Nobel Prize this year. And my task was to tell you why the work that people did for the Nobel Prize was interesting. So let me not try to answer, but just to say that a black hole, like I said, does not give out anything. Okay, as far as classical physics is concerned. But what Hawking showed in 1974 was that if you take the quantum nature of matter into consideration, then it's possible that black holes would actually radiate matter like a black body. And so you will associate then a temperature with a black hole. And of course, if it's radiating matter and radiation, then you would expect the black hole to lose energy. And if it loses energy, it loses mass. If it loses mass, the Schwarzschild radius shrinks. So the question then is that if this shrinking continues, will the black hole evaporate? Okay? Now, evaporate means disappear into nothingness, leaving nothing behind except some heat. The trouble with this is that initially, when the black hole formed, I told you already that this was a collapsing star. I showed you some pictures. Stars have atoms and molecules in them, and these all collapsed gravitationally to form the black hole. Now, these atoms, etc., particles, electrons, protons, neutrons, they are described by quantum mechanics in a formalism in which they are called pure states. So they have a rather simple way of looking at them. But when after black hole evaporation, you're left with heat, you see, you can't describe heat in terms of these simple pure states. So black hole evaporation would mean that you have a transition from something which was made up of pure states to something where you don't have pure states, but you only have mixed states. And this kind of a transition is forbidden according to the laws of quantum mechanics. So this is precisely the nature of the information loss paradox. That, if you do allow black hole evaporation like Professor Hawking would want us to do, then you violate the laws of quantum mechanics. Okay? So this is Hawking information loss paradox in a nutshell, right?
Okay, so one more thing. I think Shayankor has something to say in the comment section of our Google Meet. So you can just check it.
Please. Oh, okay, chat.
In the chat box, you can just take a look.
Yeah, so this is a quantitative description that the shadow at the center, which is slightly bigger than the photon sphere. The photon sphere is 3 times the mass of the black hole. Okay, so that is good. Yeah. So I did not talk about the M87X as a passing reference, but you're right. So this is Singe's calculation from about this is in agreement. So this is great stuff. Thank you very much. Yeah. Okay. Thank you, Shan.
So finally, one last question. It is from Dheeraj. So he's asking that in our galaxy, from the simulation that you just showed, that there are moving stars in highly elliptical orbits.
Yes.
So is there any chance in future that from those stars we can get some kind of accretion, like if they come close to the black holes, something like that?
Yeah, okay. So that's the point, right? I mean, there are many reasons why the supermassive black hole, our local friendly neighborhood supermassive black hole, is not accreting. There's probably not enough matter around it for it to accrete. Or there could be other astrophysical reasons which I don't know. But you're absolutely right. If there is stuff to accrete, if the stars come close enough, then you would see an accretion disk, and then we will have an active galactic nuclei right in our own galaxy, which will be great, because then we can study much more, like I said. And the M87 type of studies can be made with much more ease. So one is waiting for it. And it's kind of bad luck, you see, that our own center guy, the Galactic Center fellow, is not active. I mean, this is a bad luck. I mean, if it did, then you would know so much more about supermassive black holes. Absolutely correct. Yeah. Any other questions?
So there are questions coming in, but we are a little tight on time. So I think that's all for today. So if there are any more questions from our YouTubers, so you can just mail us at Project Cantilever, and we will get you with the answers. Okay. Okay, sir. You can.
Yeah, Kaushik, follow.
Okay, I could have asked this question later, but I guess I'll not see you for a couple of days, months.
Well, it may be sooner than later, but anyway, ask your question. Yeah.
So you showed this 4 assumptions of this impossibility theorem of Penrose. That 4 of them.
Let me try to get there. Yeah. Okay. So.
So 4 of them are simultaneously correct. So
right.
Is there?
No, but I should tell you, Kaushik, for you, I should say that this is my paraphrasing of the actual conditions.
Sure. No.
Yeah, okay, so they're very badly written as far as you are concerned. They're mathematically
I know this is a technical question, and I should have probably waited in fact until the time I saw you. But
right.
Yeah. So the question is that how many of them can be simultaneously satisfied? Is there a theorem to that?
Yeah, for instance, if you drop the idea that there is a trapped surface, then it's okay, right?
So 3 of them could be satisfied.
Yes, yes. So there are subsets like this which are okay. But then if you're willing to forget the first one, which is the smoothness condition,
Then I guess,
you're-
yeah.
yeah.
That's
So there are subsets which are self-consistent.
So if I sacrifice, because okay, this is related to this earlier questions. If I sacrifice smoothness in the sense of infinite differentiability, I probably can satisfy some more.
That's right. That's right. So yes, I mean, if you now require I mean, again, like I said, this is the first paper on the theorem, and it has now opened a Pandora's box. There are at least 1 million papers. Well, there are the great authors are Robert Garching and Stephen Hawking, in addition to Roger Penrose, and they have many papers. Many of them uses Rye-Choudhury equation, and they have a whole series of theorems. So this is. And now, of course, it has gone back, and these theorems are being revisited because people want to see where.
Well, other name one should mention is Christodoulou in this.
Christodoulou, yes, of course, absolutely.
Yes. Yeah. Anyway, it was a very nice talk. Actually,
thank you very much. Thank you very much.
Okay, so stay safe.
Okay. So Akash.
Yeah. So basically, thanks for the talk. It was a very lovely talk.
Thank you very much.
So,
very grateful to you. Yeah.
So we would want talk like this in the future also. So we in the panel in our
there are several champion relativists in front of you. Catch them.
So we would like if you can just give some topic that you would like to discuss in for our general audience. So you can mail us at Cantilevers. So we will be really very happy to have these kinds of webinars in future, like once in a month.
I have one just request. So if for my talk, if some of the younger people have questions which maybe they were not, they couldn't ask, or for some reason or other, just pass on my email. Okay, and I shall certainly, you have my email, so just pass it around, and I'll be very happy to answer them. To the best.
Yeah, sure. I think that will be the best, and that is what they will like. So we'll just forward you with for the students. We'll just forward you the email.
Yeah.
And they can directly ask you through mail.
Right.
Okay.
Thank you.
Thank you, Partha.
Thank you very much. Oh, Sharon, thank you very much. Thank you very much, Sharon. You've stuck on till the end. I didn't get bored. You didn't get bored.
And let me also thank Akash and his friends for this nice project.
Yes, sure.
Yes, I'm very grateful to Akash and Apratim because they did a fantastic job. And I think they should carry on their work. This is great.
Yeah, so maybe
Absolutely. I will send you a mail. Okay.
Okay, sir.
Bye.
Okay. Thank you all.
Thank you
for being us with here.
And happy puja to you too.
Okay, sir. Thank you.